I'm going to tell Rose that we have it streaming now.
Streaming?
Yes.
Have we got audio?
I don't know. I see audio coming into the ATEM, but look, when I go to multi-view, you can see audio levels are a bit hot. So let's turn that down, down, down. Test, test, test. Okay, which channel am I on? Test, test, test. Oh, audio levels are here. Test. Go back to multi-view. I need to see it. Test, 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 test. Test, 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 test. Oh, test, 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 test. Test, 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 test. Test, 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 test. There we go. Those levels look reasonable. Okay.
Video set to public?
Yes, it's set to public. You'll have to communicate with Rose, whose email I gave you. We've got 4 minutes.
So I can switch from different brands.
No, you don't switch. Oh, wait. We're missing super source. Super source. Where's super source? Yeah. Oh, God. That is not right. That looks like a secondary monitor. Okay. Rithik, do you have the slides fixed now? Good? Not fixed? Okay. Phone. That's Rose's phone number. Take it down. Hello. Oh my God. Okay, now that's up. Okay, that's up. Let's try SuperSource. Quick. But it looks like that might be set to the wrong input.
3 and 4, isn't it?
I think it was 2 and 3, maybe.
No, because we set it up from the app, from the software control.
Yeah, so we're not going to be able to do it without the software control.
Yeah.
And now we've lost video. Oh, there, it's back. Okay, you'll just have to switch it.
Okay.
I don't think anything. Have you taken Rose's number down? Did you take down her phone number?
Yes.
Okay. So you can text her to get that set up. Hello. There are still seats in this room anyway. I don't know why we need overflow. Okay, give everyone 1 more minute. Did you send me a video?
Yes.
It didn't make it in. Oh well. Sorry.
They sent you a Slack message.
That's probably why I missed it.
And I sent it on Google Drive. I wasn't sure if it worked, that's why I sent it.
It doesn't matter.
I'm in here at least. So.
Yeah.
You don't get like the Slack DM notification.
I did, but it's just hard to keep track of things when people are sending me individual Slack DMs about their thing.
Probably because people join the issue.
Yeah. Rithik, we good to go? Rithik, ready?
know the slides have the same problem again.
What problem?
The multi-view thing.
I'm super excited to join you all on your computing journey. Super excited to get to know you all. I'm really excited to be part of your journey and help you along the way. This is the first problem subject, and also the most interesting and memorable. Computer skills are so important in such a wide range of areas. Can I really enjoy that computer science instead of bringing so many fields together? I hope that you enjoy the course, you learn something new. I hope you find Python programming as useful and enjoyable as I do. And don't forget, remember, programming is fun. 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 Programming is fun.
Good morning, all 500 of you. I'm Dr. Shanan Connie, and this is Foundations of Computing. Can we have a round of applause? I am so excited to be here with all of you as you start on your journey towards learning about programming and eventually even a little bit about computer science and algorithms. I also teach Foundations of Algorithms in semester 1, so for those of you who are lucky enough to pass the subject, which I hope will be all of you, you will also see me next semester in your subsequent class, Foundations of Algorithms. So look forward to that as well. So before we talk more about the subject, I want to find out a little bit more about all of you. So I looked up on our allocation system earlier today, and there are more than 3 degree programs represented. We have some exchange students. Hands up if you're a foreign exchange student. I see a couple of you in the crowd. Bachelor of Science, Diploma of Computing, Commerce. Anyone else? What are you doing? Biomed. Awesome. And what was your name? Bassett. Awesome, so glad to have you in this class, and we'll meet many friends and faces along the way, and we're going to try and get some of you down to the front of the classroom to try and get a little bit of interaction and exposure throughout the semester. As I said, there are more than 500 of you enrolled. I think at current count we're somewhere close to the 700 mark, which means we have more than 30 staff members involved in this subject as well. So let's start off with a little quick poll about who all of you are. So A is you're competent, but you've never coded or seen source code before. That's all fine. B, you've seen source code, but you don't know how to use it. You don't know how to read it. C, you have experience with coding, but only that you've maybe played with it once. D, you can look things up and code something. E, you can code a little. And F, the computer is putty in my coding hands. So fire that up, and I am going to open up our poll. Give me a second. And we will see the results as they come in, hopefully, at that link. Okay, if people are having trouble getting onto it, no, there we go. I've got a response. So we have some coding masters in the room, some people for whom this is brand new. Typically, we expect that roughly 2/3 of the class never will have programmed anything at all before. So this seems pretty representative. The number of code mavens is dropping down as we get a few more responses. There are a couple hundred of you in the room, so I should see these numbers going up quite a lot. I'll let it settle for another minute. And we can see from our results here that for the bulk of you, this is brand new. But don't worry, we teach this class with the expectation that you come in with a fresh look. Come right in, there are seats everywhere. So what about us? Well, we have 2 head teaching fellows. and 1 deputy head teaching fellow. Our lovely deputy head teaching fellow, Rose, is right now in the overflow room in case this room gets too full, helping set up the live stream. And we have Iga and Han, who are our head teaching fellows. Hopefully someday some of you will as well become part of our staff, and that's really the hope here. Many of our teaching staff are actually undergrads at this university right now. They've completed the course and passed it and done fairly well, but also indicated that they've been good at teaching, and so that's what we're looking to get all of you involved with later. So on that note, we have 13 teaching fellows, and I managed to get at least some of their photos over here, as well as our 7 first-year fellows. Our first-year fellows are going to be appearing in the first-year Learning Center every single day to help out with any queries you have on a drop-in basis. See the Week 0 video if you have some more questions about that, and we'll make some announcements on Ed to help clear that up as time goes on so that you can find and get help when you need it. We do have 1 production associate. Now I want a big round of applause for Rithik, who's right over there. You'll often see, if you come early enough, you'll see Rithik and I chaotically trying to make everything work. Some days it works, some days it doesn't. We've got a new setup, at least for the early start of semester, because we're trying to live stream it out. I don't think it worked 100% today, but hopefully we'll get it later on. But also Rithik is responsible for making sure that we have very high quality videos, like some of those for the fancy classes that you've seen online. They will take a couple of days to come out because we have to obviously film it and then edit it. But hopefully you'll look forward to seeing Foundations of Computing in 4K, ultra high definition, with some good audio, so look forward to that. We have 1 workshop coordinator who you'll probably be getting some emails about for around things like AAPs and extensions. She handles all of that. She's amazing, but largely does stay behind the scenes. And so at the end of the year, I want us to give her a big thank you for all that she's going to have done for us. And finally, we have our 3 subject coordinators. So there's, of course, myself, and I want to introduce to you Associate Professor Giuseppe Barca. Can we have a round of applause for him?
Hello, everybody. I'm very excited to be here and welcoming all these new people to the Foundations of Computing. You will be seeing me probably in the second part of the course. We'll be contributing with a slightly more advanced topics on Foundations of Computing. And with that,
we'll turn it back. And 1 more round of applause for Professor Varka. And we do have 1 of our teaching fellows who also came here to say hi. You want to introduce yourself a little, say who you are?
Basically, one teaching fellow is I am 11 to 1 p.m. Monday tutorial and 12 to 2 Friday tutorial. Maybe seeing around if you're in that class.
And thank you. Round of applause for her as well. Okay, so that's a little bit about who we are, but what about what we do in this class? Now, one thing I'm going to bring in a little bit into our class, as you can see my very proud t-shirt, I did teach CS50 in the past. CS50 is a well-known international course taught by Harvard University, and we're going to be drawing some inspiration from that class that I previously taught in our classroom as well. So watch out for the duck icon on some of the slides that indicates material that I've adapted from CS50 that I previously taught. But one thing that's quite important to me is thinking about why you're actually here. So of course you're here to eventually complete the subject, get your grades, get your degrees, but as Professor David Malin, who teaches CS50, says in his class, what ultimately matters in this course, and Foundations of Computing as well, is not so much where you end up relative to your classmates. It doesn't matter whether you get the H1 or a pass. What matters is how you've improved over the semester. Have you actually learned something? And that's what I am looking for. Because I've had many students in the past who, like, at the end of the semester, they do okay, they pass the subject, but ultimately they're not feeling very confident. Sometimes it takes years to gain that level of confidence because it's a skill. Programming is a skill just like any other. So think about piano. Everyone's seen like the 3-year-olds on YouTube who like hit the piano and suddenly they're maestros. Unfortunately, that is not how I grew up. I tinkered on the piano as a 3-year-old and made terrible noises, and it took me something between like 10 and 20 years to actually gain competence. And the same is true of programming. Some people will sit down at the computer and suddenly it will be putty in their hands. But for many of us, programming is something that takes a lot of work. It takes skill, it takes practice. So regardless of how far you get at the end of 12 weeks, what matters is if you're on a path to learning, on a path to developing.
And as you'll see in the coming weeks, as you write your own code and solve your own problems, what ultimately matters in this course is not so much where you end up relative to your classmates, but where you end up relative to yourself when you began. And it really is all about that delta, whether you're programmed or not, just getting something out of a class like this. And if it does take time, and if you do feel those frustrations, but you simultaneously eventually feel that sense of accomplishment, that just means it's all working, and indeed, hopefully, all the more worthwhile and gratifying ultimately as a result.
So, what have I got up on here? Anyone know what this is? So, who said that? Okay, your victim number one, what's your name?
Tim.
Give a second for it to connect. The light will turn green. And don't bang on the microphone. Yeah.
Tim.
Okay, so Tim, what have I got up on here?
Box.
What else is a box?
Square.
What are we doing in this class?
It's a computer.
It's a computer. Very well. So what am I missing from this picture?
Everything.
Like?
A screen, a keyboard, everything basically.
Does a computer need a keyboard?
It needs an input device.
Okay, so, well, let's start with our output device. Maybe we do need a screen. But, as you suggested, we might need at least an input device as well. So here's our computer. I think that picture's looking a little better. So give me some examples of some input devices.
Keyboard, mouse, microphone.
And some output devices?
Screen, speaker, printer.
Great, that sounds good. Okay, so is that all we need? Taylor Swift? Oh, okay. Sorry, I've still got my mind in the Eras tour. It was excellent. She's not coming back. I'm sorry if you missed it. So what are we missing from this picture still?
Everything that turns the input into the output.
What do you think we might call that? Does anyone else have an idea of what we might call the thing that turns the input into an output? Okay, I see a hand over here. What's your name?
My name is Tom, so that's funny. We need a CPU.
A CPU? Okay, so let's think a little more abstract. A CPU is a central processing unit. It's the chip that processes instructions. What else are we missing?
Well, CPU, a clock, memory.
Come sit down. No worries at all. But what actually turns the input into the output on an abstract level, not on a physical level?
Would it be binary operations?
So that's still getting very down into the weeds of actually how we're building the thing. But more abstractly, we want some process. We want to be able to describe some set of steps that take us from the input to the output. So actually, we'll save this for a little later. So the first thing we need to do, as you might say, was Tim? Tom. Close. One letter off. We are going to need to figure out a way to actually get stuff into the computer and get stuff out of the computer. And the word we're going to use to describe this process is representation. So you said something before about the way that computers represent things. What was it? You used a word. Binary. Who knows what binary is? Put your hands up if you heard of binary before. Leave your hands up if you know what binary is. Okay, let's take one person from over here. Okay, you had your hand up? What was your name?
My name is Elizabeth.
Elizabeth, okay, tell me what binary is.
It's a system where you can either have things like on or off, 1 or 0, and then it represents
Yeah, that sounds pretty good. So let's start with something even simpler. If you know what binary is, can you guess what unary is? If bi is 2, unary is 1. Okay, so can you show me how you count in unary? Okay, so let's start off. Let's assume we only have one possible digit, and that digit is the number 1. So how do we count to 2? And then how do we count to 3? And how do we count to 4? And how many digits are we going to need if we want to count to 1,000,000? We're going to need 1,000,000 digits. So obviously unary has got some serious limitations there. Plus it also doesn't allow us to represent things that are off. It only allows us to represent things that are on. And that seems pretty challenging. So unary is what we call base 1. There is only one possible symbol that we can use to represent our numbers. But as Elizabeth said, we actually want to work in binary, which is base 2. Okay, so now what are our options? Elizabeth, what do we got?
0 and 1.
So now we've got 0 and 1. So if we start counting, what do we start counting with? Give me the numbers. So what's the first number in the numbers? 0 sounds pretty good. Okay, so how would we represent 0 if we have a 0 and 1 as our possible symbols? 0 sounds good. We can just use 1, 0. We don't need 2. What about 1? Okay, so we haven't really made any progress so far. It seems like we're doing the same thing as before, only now we've got the number 0. But let's push this a little further and see what happens. So we're going to be talking about this semester in terms of binary digits, which is the long way of saying a bit, a binary digit. And this is the fundamental unit of computation that computers, or the computers that we use, are going to run on. They're going to have switches inside of them that are either on or off, and using these bits, we can represent a whole bunch of different things. So we have our default off state, which was, remind me, 0, and we have our on state, which was, and just by using these two things, we can actually represent any type of data we want. So if it is a Taylor Swift song, or if it is a video game for an Oculus Rift, or if it is a movie that you want to watch, all of these things, at the end of the day, can be represented just by using these two symbols. However, we're probably a little more used to operating in base 10. So who can count to 10 to me? Can count to 10 for me in base 10? Just
1, 2, 3, 4, 5, 6, 7.
yeah, so that seems a little bit easier. Now, what if I asked you to do it in base 11? What do we do then? Who said that? Okay, you've exhausted your light bulbs for today, so you know what's going on. I'm going to need someone else. Someone else? Tanisha. See, this is the danger with telling me your name. Okay, so what do we do to count to in base 11 after we get to 10? After we get to 9, what comes next? We need a new symbol. Okay, so what symbol might make sense for us to use when we've exhausted the digits 1 to 9? 0? Well, 0 to 9. That's very clever. You got me out there. So assume we've used 0 to 9. That's our base 10. We've run out of those characters. What can we use as another character? Alphabet. Okay, so where should we start? A. So that's good. So let's say we're in base 11. We might decide to augment our characters 0 to 9 with the letter A. So we'd count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A. But now I'm at the end again, right? And I'm struggling. I don't know what the next number is. What's the number that might come after A? Well, I said you've only got 11 symbols. This is base 11. So instead, we've got to start reusing some of our symbols. So when we do base 10, when we hit 9, we do a reset, right? How do we reset? What's next after 9? 10, which is the same as if you were to talk about the symbols we're using. 1 and 0. Okay, so when you exhaust your symbols, the rule seems to be move one place along to the side and add the first symbol again. So if we get to 9 and then we get to A, what would come after that, Tanisha?
1, 0.
1, 0. Okay, but 1, 0 is no longer 10 because we're operating in base 11. And so this gives us a flavor of how different representations can be used to talk about actually the same number, just writing it a different way depending on the number of symbols we use. So our base 10 representation we're going to call decimal, and will be one of the other really common representations, and we're going to switch in this class between a variety of different representations. Sometimes we'll use base 16, which is known as hexadecimal. Sometimes we'll work in binary, base 2, and sometimes we'll work in base 10, which is decimal. So just like we said before, this is now the ones column, we have a tens column, and we have an hundreds column. When we reach the end of our symbols, because we're working in base 10, the next column over is multiply the prior column by 10, and that gives us the value of a 1 in each of those columns. So to add this up, it would be 1 by 3 plus 2 by 10 plus 1 by 100. That is equivalent to 123. So we can also write that 100 plus 20 plus 3. Now, what about this? Who knows what this is? Someone new? Okay, let's get the microphone all the way back there. Elizabeth, can you pass it back? Or, oh no, Tanisha has it, sorry. I forgot, we already finished speaking to you. It's a laughing emoji? Okay. How do you think the computer represents a laughing emoji deep down inside? Is the computer laughing somewhere inside the CPU?
Definitely has a code for like the color and structure.
So one way of thinking about it might be as an image. But another thing is the emojis that we use, they're just like letters on a keyboard. If you go on your phone and use the emoji keyboard, it's not treating them as pictures, it's treating them as letters. Just like the letter A, you could either represent as an image made up of lots of different little white dots that when you view those white dots from far away, they look like the letter A. But you can also represent it as a number, or the number 1, same thing. You can look at it as a bunch of white dots, or you could represent it as a number. So it turns out under the hood, the way that computers represent most emojis, the ones that at least appear on the emoji keyboard, is as a number. But let's also talk about the picture version that you were talking about, what we're going to talk about in terms of red, green, and blue. These are the 3 colors that computers typically use to make up any image. So you said that we could represent our emoji as an image. So if I ask you for, say, this part of the tier, the blue tier, how might you represent that if I told you could only use red, green, and blue?
I think there is a binary or an hexadecimal code for it.
So even before we get to what the computer might do, what would you tell me if I asked you to represent the tier using red, green, and blue? It's blue? Is it 100% blue?
No mixed with white.
It's probably got a mix of some of the colors in there as well. Like we can see bits of it are closer to white, and some of it is a bit closer to dark blue. So what we could do is assign each of the little dots in this picture a different RGB value, telling us for each dot how much of it is red, how much of it is green, and how much of it is blue. Now, we could do this for these particular colors, and we could say 72 out of 255 red, 73 out of 255 green, and 33 out of 255 blue. Now, you might ask me, like, why out of 255? That seems like a really odd choice. Well, let's go back to our binary representation for a minute and start doubling numbers. So we start, the ones place is just ones. The next place along, if we move, remember how I said we had the ones columns, the tens columns, the hundreds columns for base 10. So let's do it for base 2. So we have the ones column. What's the next column? The twos column. Then the fours column. 8. What comes after 8? 16, 32, 64, 128, 256. Now 256 is pretty close to 255. Why might I be talking out of 255?
Because we start counting from 0.
Yeah, this is a great point. Tom?
Yes.
Tom said, well, actually computers start counting from 0, so even if we have room for 256 different combinations, the very first combination that we have is where everything is set to 0. And so as a result, if we are using we're using enough room for up to 0 to 256, we have to remember to save the number 0 aside, and so the highest color value we can get is 255 out of 255, with the first option being a 0 for that color. So now we could look into our emoji in a little more depth. We could open it up in an image editor and zoom in, and zoom in. Oh, there we go, and zoom in. And now we see our pixels. These are the individual dots that are going to make up the image. Now for a higher resolution image, when you talk about like, this is a really high resolution photo, that means that you have to zoom in further and further and further until you see these dots, because it's zoomed out a long way and packed more of the dots into a smaller space. And this is how we actually represent images on a computer. This is the simplest way. And indeed, already you could draw a picture for a computer by writing out these values. Now there are a couple of steps to go from writing out the values by hand in order to get the computer to actually translate it, but not as many as you would expect. And perhaps sometime during this class, we will actually show you how to do that process. So now we are back to our model of computers. We've figured out how to do the input. We've shown you at least some of the output that you can get, perhaps in terms of images. but we're still missing this process in the middle. We're missing something significant there. And that is going to be our algorithm. And an algorithm is just going to be a defined set of steps for converting a given set of inputs to a given type of outputs we want. And we'll talk a bit more about that as we go along, but you can think of it as a procedure or a set of steps that's systematic, that applies to more than just this particular input. It applies to a class of inputs. So for example, if you have a scheduling problem, you want to figure out when to put the different classes in the university timetable. We don't care about the particular set of constraints that Melbourne University has. We want to come up with a procedure that would work for every different university. What are the set of steps that take a set of constraints of classes to be timetabled and produce a list of which classes should go into which time slots? And that would be an example of an algorithm. So to do a demo, I didn't get breakfast this morning. I've been up since 5 a.m. working on this. And so I brought the ingredients for my sandwich. I have my inputs, and the output that I want is a sandwich in my belly. So I need one volunteer who's going to help me out with this. Okay, come down to the front. Let's get the microphone all the way back from, what was your name again? Gia. Okay, so can we pass the microphone back? And I need a second volunteer as well. Okay, come down to the front. Come on, we can do a better job with this microphone passing. There we go, there we go. Here, I got it. Okay, down to the front. Okay, let's come to this side to make Rithik's life a little easier. And what was your name?
My name's Gabriel.
Gabriel, let's this on. Test, test, test. Test, 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 test. You're going to need to hold this really, really close.
My name is Max.
Okay, so which one of you wants the brain? Do you like brains?
Yeah.
Okay, so Gabriel. Okay, now you're going to need to help him hold the brain. So that's unfortunately your job, is to hold the brain and hold the microphone. Okay, now let's spin this way so that everyone can see us.
Hello.
Okay, come back a little. Now we've got our exercise to do. So let's see. We'll use this as a table. This is going to work fine. And I'm just going to put this here. Okay, I have bread, I have peanut butter, and I have a knife. These are the three inputs to my function. And Big Brain, I've got a question for you. So pass on the microphone. How do I make a sandwich and eat it? You'll have to look this way.
Open the bread bag.
Okay, open the bread bag.
Take out the bread with your right hand onto the right hand. Lift it up. Release the bag on your left hand onto the floor. Pick up the knife with your left hand. Stab the peanut butter jar. Put down the bread. Put down the knife. Release the peanut butter jar. Pick up the peanut butter jar. Hold it straight with your left hand. Open the peanut butter jar with your right hand. Longer. Twist the lid. And throw the lid out. Pick up the peanut butter jar again. Twist it the other way. Twist it again. your left hand. Stab the knife into the peanut butter jar. Twist the knife. Take the knife out. Put the peanut butter jar on the chair. Do not throw it. Do not throw it. Pick the bread up with your right hand. Spread the peanut butter onto the bread. Do not throw the bread. Spread the peanut butter on the white side of the bread. Yeah. Spread it on the same side of the bread using the other side of the knife. Put the knife on the chair. In the peanut butter jar. Fold the bread in half. Eat it.
Bread's been on the ground.
Oh.
I need more instructions.
The sandwich is finished.
I haven't eaten it yet.
Put the sandwich. Put the bread into your mouth. Open your mouth. Do it again. Tilt it and put the bread in your mouth sideways. Bite on the bread. Pull it out. Repeatedly bite on the bread. Pull the bread out. Do not approach the bread to your head and continually biting it. Swallow the bread in your mouth. Do it again. Put the bread to your head again, to your mouth again. Put the bread sideways into your mouth. And bite.
Our regularly scheduled programming will resume momentarily. Thank you very much. So, as you can see, programming is a little hard. This is an example of an algorithm to eat a sandwich. However, you could see that at different stages, the specificity of the instructions that we were given impacted my ability to compute the instructions successfully. And computers are just like this. They're going to take what you write very literally. So if you don't say, rotate the sandwich 45 degrees, slowly insert it into your mouth at a gentle speed, insert only the end of it, and then bite down gently, you're going to get a result similar to what you just saw. I probably still have peanut butter everywhere, but we will just have to live with that for the rest of the lecture. Now, we could also talk about the process by which we used to arrive at that algorithm and the different types of instructions that I was being given. So the kind of instructions that our computer is mostly going to be working with, we call code. Now, you may have seen people talk about, we have codes. Codes are typically not the word we actually use to refer to the plural of computer code. The plural of computer code is typically code, and when people say codes, that typically refers to hidden messages and ciphers. So that's just one thing to note when you're asking us questions. Try to remember, plural of computer code is code. But the code that I was running was not quite computer code. It wasn't written in any programming language that I know. The programming that I was following was much closer to what we'd call pseudo-code, which is a description that humans can understand of the instructions that you might give a computer. Now, as we saw, there were different levels of specificity at which I was being given the pseudocode. So one example was open the bag, and that resulted in me like tearing it apart sideways because there wasn't enough specificity in what open the bag meant. At a high level, we could understand that as one instruction, or we could understand it as being composed of lots of sub-instructions. And this is going to be one of the challenges in computer science, is figuring out the right level of specificity for a given task, and then saving bits of your code over to the side for you to use as what we'd call functions. These are reusable tasks. So for example, open a bag might be a bit of code that you would write so that it wouldn't just apply to the bread bag, it might also apply to my backpack or something like that. And you would write code that's reusable that we call a function to perform that procedure over and over again. So that when someone says, open the bag, you don't have to go into all the minutiae of the correct way to open the bread bag. So here is an example of a high-level version of the peanut butter sandwich algorithm. So 1 would be extract 2 slices of bread. 2, if the jar of peanut butter is closed, open the jar. 4, use the knife to scoop peanut butter from the jar, etc. But these were more or less the instructions that I was given the first time, and they didn't work as well because we hadn't defined some of these substeps, some of these functions. So for example, extracting 2 slices of bread was underdefined. So I've written now a longer version of the pseudocode that has more details about how we might perform some of these steps. So for example, how to eat the sandwich has been subdivided into cut the sandwich in half, pick up 1/2 of the sandwich, take a bite of the sandwich, chew thoroughly, swallow the bite, etc., etc. But even this isn't quite enough instructions, at least for me, to have gotten all the way to have eaten the sandwich. So I decomposed my sandwich into 50 steps. So extract the 2 slices of bread, open the bread bag or container, reach in and take out 2 slices of bread, etc., etc. I'm not going to read out all 50 steps, we've just been through that. But when you are doing your own programming exercises, this is a helpful step for you to do. Take a problem, maybe break it up into 3 instructions, or 2 instructions, make the sandwich, eat the sandwich. Decompose each of those instructions into their sub-instructions. Decompose each of those into the instructions that make those up all the way until you've gotten to a point where you have a set of simple steps that you are actually able to write about in code. So even though we've only talked about pseudocode for the moment, this same process applies to your thought process when you are actually going out there solving problems. So here's another algorithm to find the student in the class who has the largest student number. And we're going to come back to this example a few times because we're actually going to try write this one in code. So my procedure, my algorithm for finding the student in the class with the largest student ID might look something like this. Connecting. Wait for the light to turn green. There we go, it's green. Okay, what's your student ID? Just give me the last 2 digits.
63.
63, okay. So the largest student ID that I've seen so far is 63. Okay, last 2.
64.
64, okay. So now I have to change what I've remembered. I don't have to remember 63 anymore. It's totally irrelevant. Now all I have to remember is 64.
93.
93, whoa, that's a big one, okay. So what do I do with the 64? I forget it, okay. So now I remember it was 93? 93, okay.
45.
Do I do anything with 45? No, okay.
65.
65. 71.
67.
67, okay. I'm still not doing anything because I haven't hit the condition of if the ID that I just hear is bigger than what I remembered? I'll give you a chance.
55.
55. Okay, so I'm not sure we're going to beat 93 for a while. We got lucky very, very early on. But this is an example of a procedure. So if I do this, and I go through every student in the entire room, I have a guarantee that by the end of this procedure, that I will have found the student with the largest ID, assuming that we're also not just looking at the last 2 digits, which will probably, in a room of this many students, we are pretty much guaranteed to have some conflicts there. So this is another example of an algorithm. And this one actually looks a little closer to computer code. The type of pseudocode that I've represented up here is starting to look closer to the types of instructions that a computer will use. And again, this is another step that you can perform when solving a problem, is to write it out in like super plain English, and to go step by step from the very plain English to a set of steps that you could feasibly translate yourself into code. We'll come back to this, but this is essentially what we call linear search. We're going through one by one through everyone in the class. The only difference between this and the true linear search algorithm is in the true linear search algorithm, we're looking for a particular number in the entire room, but that would have taken me far too long to do with all of you. One of the major motivating questions for computer science was, is this really the fastest way to do it? Because this is going to take me looking at every single student in the class. And this is something that we will revisit probably later in this semester, and then in Foundations of Algorithms with me next semester, in which I hope to see every single one of you. Okay, so now we have our pseudocode for our let's find the largest ID problem, and let's take it one step closer to computer code. And it doesn't really matter exactly the programming language that we're going to use, we're just trying to get closer and closer and closer to something that a computer could understand. So what we're going to do is we're going to use some funny notation, and don't worry, this will become clear later, but we are going to store the largest number that we've seen so far in something called max, and that's just the maximum that we've seen thus far. And so what we'll do is we'll store the very first student we see. What was your name again?
Alan.
Alan. So Alan's student ID is going to be stored in max. And then for every student in the class, go through them one by one, and for a given student, if that student ID is larger than the maximum, set the new maximum, and at the end, we're going to return back to the front of the room, back our answer. This is the language we're going to use for how an algorithm tells us what the answer is. We're going to use the word return. So input into the function what we want it to do, and then return is going to be the answer back. So at the end of the day, when we've finished our procedure, return max. And assuming that we've gone through the set of entire students in the classroom, when we return max, it will indeed be the student with the largest ID number. So throughout semester, we're going to need a bunch of different tools to help us to compose programs that do useful things. So some of them are going to be iteration, so how to repeat a process over and over and over without having to write the code itself over and over and over. We're going to need selection to choose from different alternatives and make decisions. We're going to need functions to break up our program so we're not stuck with having to provide every single little detail of the sandwich algorithm every time we want to do something. And then we're also going to talk about how to represent collections of data in different ways. So whether that's representing a picture through different pixels, whether that's representing a movie, whether that's just representing a set of grades for students in a class. All of these are the tools we need. Okay. So with that, let's take a pause, and we're going to bring Kat back from the back of the room to introduce herself. And as usual, this takes forever to turn on. There we go, it's green.
Okay, hello everyone. So my name is Kat Vilamova. We'll be also teaching this software together with Charlotte and Giuseppe. So I come from computer information systems. I work on natural language processing, the area that became quite popular due to large language models and ChatGPT. We now experience a lot of hype about this. So I focus on multilingual language models and data efficiency for developing language models for small languages. I also work on computational approaches to study language itself and computational social sciences. So I will see you all on Friday, and we'll discuss computability, and we'll start doing some simple exercises on rock.
Thank you very much. And now we will take a 5-minute break till 9:55. Hey guys.
How you doing?
How was it?
Well, it's been all right so far. I was very nervous this morning. Let me switch this off for half a second.
Probably leave now because I need
Yeah,
to
no
fix
worries.
my laptop. My laptop, like the work laptop, doesn't work. So like I have the COE payload issue.
Oh no.
But yeah.
We don't need an overflow room, and we don't need to be delivering this 3 times a day.
So how does it work? So there's someone else in there.
Yeah, but there are no students there.
Because they don't know that they.
No, there was an announcement that went out, but this room isn't full.
Yeah, there is still
There are lots of seats available. So we're all fine. So I think in future we can not worry about the live streaming and the as we thought might happen.
Really nice jacket.
Thank you. I was worried about getting peanut butter all over it today.
That was amazing. I loved it.
Is it your own microphone? You
Yeah.
bring your-
So that the whole lecture is being recorded in that device over there. But
What's the story with him?
Rithik is, I got special funding. He will film every lecture.
Okay.
He's got a cable that you plug into your laptop and that takes the slides, and then you plug another cable into the projector.
So we don't need basic Eco 360 stuff.
We use it as I use it as a backup. In case this all goes wrong, I'm gonna have something else. But this provides a,
Yeah.
yeah,
don't have to set it up. You just make sure you have microphone.
yeah. But this setup is much higher quality.
Would you like to try and fix your stream?
Yeah, I'll try that again. But I don't think anyone's on the live stream anyway. To ask Rose. But this thing needs power.
Yeah.
Oh, you got power?
Share the second one.
Do you want to try and share your screen instead of just because when you did the poll as well, it didn't show up.
I'm trying to do a single screen thing, but it's not working well. But no one's watching the live stream anyway.
Can you please put my PDF on the website?
It's not on the website already?
I mean, in the curriculum, like the link. We typically put the links in the syllabus.
Yeah, they should be there. The ones for today I must have messed up. I'll check out as soon as the lecture's over.
Fixing my laptop. I've got some laptop.
No worries, I will make sure it's there.
Okay. Yeah.
Did you actually get to talk to like David Mallon?
Yeah,
And everyone said-
I was at CS50 a couple weeks ago.
Okay, because I just watched like the YouTube post.
10 people.
Yeah.
He's really like,
So then you don't need as much to be in here if you've already done CS50.
I mean, I know in college it was pretty good. Just
Yeah.
10 people are watching.
10 people are watching, okay. That was not a good peanut butter sandwich. The worst peanut butter sandwich I've ever had. It's a lot of power to give a student. Hey,
Where can I find that just right?
schedule? And then, yeah.
Oh.
But I recommend not using the LMS because the LMS is annoying. Like you've seen the proper class website?
I'm using another system.
Like if you go home, and there's this link. And once it loads, so you can see the menu there. Oh, the menu there of all the different class things.
Oh.
Oh, the wrong thing. Rithik, can you check the multi-view quickly? We'll have to figure it out next time. All right, everyone, and we are back. I hope you got at least a few moments of peace. And now we are going to continue on with the second half of today. Now, as you might notice, these lectures get a bit long, so if you need to head out early or you need to go for a walk partway through, that's totally fine. The recordings will be available, and as well, make sure to use the break to refresh yourselves and all of that. The other thing that you might notice that will happen a couple of times a semester, so I'll do what we call in theatre an aside, which means it's not part of the main show, a character steps off to the side. And we can do that because we are going to be editing the videos after, so I might sometimes tell you something that won't appear in the main video, such as this little moment. So what we'll do is I'll start speaking again, we'll pretend that never happened, and we'll redo our intro to the second half of lecture. So that we just have something to capture a little more seamlessly onto the lecture. All right, welcome back, everyone. We are now going to talk about our next algorithm, which was very, very similar to the past one. I just want to see if we absorbed it a little bit. So I need another volunteer. Okay, we got one all the way back here. Now, this is going to be a little hard to catch. Okay. So what was your name? Seb.
Yeah.
Right, okay. Oh, we do have camera, great. So Seb, this is our question for now. I want you to come up with some pseudocode for how we would look for a specified number in a set of numbers. So this was linear search that we were just talking about.
Okay. Are there any other details?
That's all you got for the moment. Very high level version of the problem.
All right, we'll probably want to look at the characteristics of the specified number, and then...
So let's say the number that you're looking for is 37. You want to see if 37 is in our list of numbers.
Yeah, we'll go 1, and it'll be if number is if our number is specified number, return number. If not, move to next number.
Okay, that seems pretty reasonable. So let's imagine that we have boxes with numbers inside. And so while there is a box left to check, what are we going to do?
We'll
check the box,
yeah.
Right? Okay, if the number inside is what we're looking for, return that the number is in the list. And if the number isn't, after we've finished this whole procedure, once we've run out of boxes to check, if we haven't found the number, what do we know?
We return false when we move to the next box.
Well, the return false is only at the end of the day. That's once we've checked all the numbers. We can't say that the number isn't in the list if all we're doing is checked one number.
Yeah, no, that's understood. We move on, and then until we find our number. Unless it's not there, then we return false.
So you'll note one thing about the pseudocode. I'll grab the microphone, thank you. You'll notice one thing about the pseudocode I've written up here is that there is an indentation of certain parts of it. And what this means, at least in some programming languages, such as Python, the one that we're going to be learning, is it helps organize our thoughts into different groups. So we've got what we call a while loop. We're going to do this set of actions as long as there is a box left to check. Which actions do we want to do as long as there is a box left to check? Everything that's indented past that line. So we can see that it seems like there's a group of instructions that are connected to the while, and then there's an else that kind of comes after that. Oh, that's indented poorly. Let me fix that up. There we go. Now my code is correct. Sorry, these slides are brand new, some of them as early as 5 a.m. this morning. So now we can see that we have some of the instructions are grouped next to the while, and then at the end of the day, when the while is done, then we can return false. Why do we return false whenever the while is done? Well, we know that if the number was somewhere in one of the boxes, that we would have reached this return true earlier. If at least one of the numbers in the set is this target, then we'll hit the return true. And what return is going to do is it's just going to stop the processing right there, because we already have our answer. We don't need to do any more work. And so in the programming languages that we're going to use, a return ends the current algorithm, or ends the current procedure, or ends the current function. So it jumps out, and we finished with all of those instructions as soon as we hit a return. So when we find a number that matches, we return true. Yes, the number we're looking for is in there. And if that never happens, if we've been through all the numbers and we still haven't found the one we're looking for, then we're going to return false. And you can see that return false is back indented all the way out again because it's not part of the while. It only happens after the while is finished. But don't worry if this was a little much for you. We're going to go into more depth into iteration, which this is an example of in subsequent lectures. And we're also going to talk about how to do this in actual code. There we go. So there are lots of different programming languages, and what I've shown you so far isn't really any of them. It's more just high-level descriptions of the way a programming language might work, and then you could always translate these instructions that we've been showing up into the specified syntax and semantics of a given programming language. Syntax is, okay, how many spaces do you have to put? What symbols do you have to use? And semantics is the actual underlying logic of the way a given programming language works. So you can go from your pseudocode, and if you know the syntax of a programming language, you can write it in that correct syntax, and then use the semantics of the language to make sure that you've actually got the logic correct. So here are some examples of some different languages in which we might implement this pseudocode that we've already talked about. Now, please do not worry. This is just to show you what they look like. We're not going to expect you to learn all of these different languages. Indeed, I don't think Giuseppe, Kat, and I each know all of these different languages. Have you ever programmed in PHP before? Not really. Not really, okay. I programmed in PHP once when I was working at Meta, but since then, this is now Greek to me again. This is C, the language in which we teach foundations of algorithms, so kind of verbose. This is JavaScript, a language that many of you might have heard of, or indeed some of you might have used in high school. It's one of the languages that powers the internet. This is Java, another variant. JavaScript is a variant of Java, and here's the code again, also kind of verbose. Assembly language. Now this language is kind of interesting, and this is where I'm actually going to take a moment's pause. Assembly language is a rather special language because it's much closer to what the computer actually understands. Now what do I mean when I say what the computer understands? After all, the computer is a machine. So if we were to open up the computer and we were to take a little, who here is doing physics? Anyone doing physics? Okay, so if I take a little oscilloscope or a voltage meter and I attach it to different parts of the computer, I could actually start to measure ones and zeros, which is something you might do in an electrical engineering class or in a physics class. And so when I say what the computer understands, what I really mean is the chips that are running the computer, the individual circuitry, has certain sets of ones and zeros that it operates on. So if you were to feed in 101111001 and into the chip, you might produce a voltage at the other side that's like on, off, off, if you were to measure those individual wires. And what assembly language can do is it can be represented directly in a form of these ones and zeros, which can then be translated into voltages along these wires, or really onto settings of transistors. Transistors are electrical components that behave as switches. So we can go all the way from this assembly language, which if you were to zoom in on the slides at home, you can see these Englishy, well, vaguely Englishy looking things. There's a table where you can look up, okay, vaguely Englishy thing, what setting of the switches? And so if you put those settings on the switches and then you measure the output from those switches, that's the same thing as running the program. And so assembly language is very, very close to that raw ones and zeros. So what's actually happening at the end of the day when we run a language like Python is under the hood, the computer is doing some kind of conversion process to take something that looks a little simpler, a little more familiar, and a little more English than the assembly language, converting it into the assembly language, converting the assembly language into that ones and zeros, and then feeding those ones and zeros down the circuitry to get the outputs. So out of all the languages that we've looked at, Python at least seems to take the least room. So now we're going to do a quick poll just to see if all of you are awake. Which programming language seems easiest to read out of all of these? So I will open up that poll. Wow, you guys are well ahead of this. You were doing it all along. So we can see Python wins by a mile. Who are those of you who are picking assembly language, that 3.11%? Put your hand up if you picked assembly language. You picked assembly language? That was a crazy decision. Okay, let's go back here. Okay. So one of the reasons that we choose Python to teach in, at least for our very, very intro class, is that it is relatively easy to read. Now, this doesn't mean that I'm expecting all of you to be able to look at this, tell me how it works right from the get-go, but at least in terms of all the other languages that we've looked at as potential options, it's the one that at least seems the most approachable. And indeed, this is why programmers in real life often use Python for tasks that only need a little bit of attention and they want to do very quickly. Now, Python does have some trade-offs. It can be a particularly slow language, so if you're doing something very high performance like Counter-Strike, anyone, or any other shooter video games anyone play, Call of Duty? I only see 3 hands, that's got to be a lie. What about a Nintendo Switch? Who has a Nintendo Switch? Okay, I see a few more hands. So if you're doing something that requires like heavy processing and lots of graphics and generating lots of images on the screen, Python might not be the best choice for you because the process of converting this into the settings for the switches actually takes the computer a considerable amount of time. So if you're doing something like that, you might code in C, or if you're really worried about a particularly small part of the program and making that small part of the program really fast, you might even get one of those mavens who can handwrite assembly code. Now, most programmers in the world, most computer scientists, actually don't know how to deal with this. It's something that maybe you will have seen once in your undergraduate computer science course. You will have written a few programs in it, but it's actually a valuable skill to have to be able to span the gamut of languages all the way from something very easy and simple to write like Python, that's a bit slow, down to assembly, which is very fast, but has this kind of arcane syntax that's hard to read and hard to write. But because all of us are a little new to programming, we're going to start off with something even easier than Python, and we're going to start off with Scratch and a language called Blockly. Now, both of these are graphical programming languages that allow us to do our programming by dragging elements around on the screen. So what I'm going to show you in class will be Scratch, and what you'll do in Grok, our online learning platform, will be Blockly. But the same principles apply, and what you can do in Scratch, you can generally do in Blockly as well. The reason I'm going to use Scratch, at least in class, is because it provides a really nice visual, whereas Blockly is a little more limited in the way it's implemented in Grok. So we're going to visit scratch.mit.edu, and I encourage all of you to play around with this in addition to doing the Grok worksheets. So let's start with our very, very first program. So you might have seen in our intro video, I talked about the very first slide, the very first words were hello world. And that is a tradition in programming that we always, when we're learning a new program, we start with the hello world program. And the goal of the hello world program is very simple. It's just to display the words hello world on the screen. And the terminology that we're going to use to talk about displaying words on the screen is printing. This is terminology that comes back from the olden days of computing, when the only way to get output from a computer was actually to print it on a piece of paper or a piece of card. So we are going to open up Scratch over here, and you can see the interface, and we have this really cute little cat, and that cat is going to be our character for the time being. In fact, we can pretend that the reason we have a cat here is because of Cat the Lecturer, but this is indeed just Scratch's default character. So let's start with our very basic program, and let's take a look here. So the first thing we need is we need a block for when the green arrow is clicked, and then we need a block for say hello world. So that is a yellow block and a purple block. So if I click the events button here, I can see when the green flag is clicked. And then let's go back to my slide, and I need a purple block. So let's go to the purple blocks, say hello. And I'm going to drag that over and just attach them. And I'm going to modify this to say hello world. So this is my very first program. Let's see what happens. So I'm going to click that, hello world. So that's great, but not particularly intelligent, not particularly sophisticated yet. There aren't that many things that this could do. So one thing that we might actually want our character to be able to do is identify the person to whom it's speaking. So let's carry on and see how we can improve our program to give it a little more functionality. So just going through some of the interface. So on the right-hand side, I always get my lefts and rights confused when doing this lecturing turned around thing, we can see all the different blocks that we could add in. Now, Scratch and indeed Blockly come with a whole lot of different options for blocks that we could put in. We can move the character around the screen, we can test for different things happening and make decisions. Then we have the main area where we're going to put all our blocks. We have a set of characters that we can choose from, so we're not restricted to just our one cat that we already have. And then, of course, we have the area where we can see the results, the outputs from our program. Now, this is also going to be true when we start writing in more text-based programming languages. We're going to have a similar place where we can see the output and a place where we can, instead of dragging in the commands, actually type in our commands and run them. So the way that Scratch is set up is it's got a grid of 240 pixels that way, 240 pixels that way, and in all directions. And so we can move our character along the grid to try and do different things. So we've done our say hello world, but now we want to actually start to create a process, start to create an algorithm to do some more interesting things. So let's say our input is hello world, our function is say, and then our output is say hello world. So we've kind of already got this very, very basic algorithm. And our task is now to maybe change both the input and change the function so that we can start to produce more interesting outputs. So how about this block, an asking block? Let's go into Scratch and find the asking block. So where is the asking block? Okay. That's the motion one. Oh, sensing. Here we are. Ask, what is your name and weight? Now, on its own, that's not particularly useful. It's not part of my program. It's just an instruction sitting out there in the ether. So let's try and connect it up to our program. So will this program do anything useful? What do we think? What's this program going to do? Someone new? Someone new, sorry, Tom. And it's going to kill me because I've already forgotten your name, but so you'll have to remind me. And there we go. Green.
My name is
Maka. Maka.
Yeah. It's just going to say hello world again.
Okay, it's just going to say hello world again. So let's try it. Let's reset the thing, and we'll run green. What's your name? Okay. Well, that's not useful. Why hasn't it used my name?
You haven't told it what to do with your name when you inputted it. It just waits and
Yeah, so we're going to need some way to store the name, some way to connect the output from the ask function to the input of the say hello world. So one thing that we can do in this language, at least in Scratch, is we can compose blocks. So let's try, and there we go. Use the join function, which will allow us to take the answer from our asking thing, join it to the word hello, and then say all of that. So we're going to compose three different things. We're going to compose the ask function with the say function using the join function. So these are three different things our computer can do. Our computer can join two words together, our computer can ask for a word, and our computer can say a word or print a word. And by mixing these things up in the right combination, we can get a program that actually does something useful. So we want the answer, we're going to join hello to the answer, and then we'll get hello Shannon. And then once we have hello Shannon, we're going to feed that into the say function, and that overall will give us our output. So let's do that now. So the join operator is in here. Ooh. Where's join? There we are. Join hello with answer. And I will put that in there and join this all up. And now I have a more complete program. So let's try this. Start it again. What do you think I'll get now? Okay, let's try that. What's your name? Ah, I've made a mistake. What mistake have I made? I'm missing a space in the join. Okay, so let's go into here. I'll put a space after hello, reset it and run one more time. And there we go. We've got hello Shannon. So we're doing well so far. Now, this is all well and good to produce basic textual input and output, but it's probably not that exciting. So I'm going to give you the opportunity to decide what we should make the cat do next. What do you think the cat should do? What would be fun? If the cat could solve a maths problem, okay. So what's a simple maths problem? Very, very simple. 1 plus 1, okay. But 1 plus 1 seems a little too simple. Maybe we want it to be able to add two numbers together. So I'm going to get you to help me put this together. Okay, so let's start with the ask function. That's how we get input, right? So what would be a good question for a maths? If we're trying to do addition, what do I want to ask the user? Enter the first number. Okay? And now what problem are we running into? So you said something useful there. What did you say? What word? Variable. So who here has heard of a variable before? Okay, so we've got a large number of you who have heard of what it is. A variable is just going to be a box inside the computer's memory that allows us to store some information on a more permanent basis. So our answer over here is very, very temporary in this programming language, and we've only got one of them. So what we really want to do is we want to be able to put that aside for later and store it inside the computer's memory, and we're going to store it in what we call a variable. So fortunately, we have a set of blocks in Scratch, and you'll have them in Blockly as well, that allow us to make these variables and save things to them. So in these orange blocks, I've now got something called set my variable, and I can choose the name of this variable. So what would be a reasonable name for this box if it's storing our first number? Number 1. Okay, so let's call it num1, and set num1 to answer. Okay. So inside num1, we are now going to store the answer of what the user input before. Okay, now what do we do? Okay, let's ask for the second number, and Okay, so we need a second variable now, and the way we're going to do that in Scratch is we're going to press the Make a Variable button, and we're going to create a second one. And we have num2. So I'm going to do set num2, and what am I setting num2 to? Yeah, answer. So answer has been overwritten the next time we asked a question. So that's why we needed the variable in the first place, was to make sure that even though there's only one answer at a time, we can still store it somewhere. So let's put that in there. Set num2 to answer. Okay, so we've got two numbers. What do we do now?
I'm guessing you go to the operator, there should be an addition one. That's okay.
Oh, it looks like there's an addition one. That's good. Okay, so I can drag that out. Now what do I want to put in this? What are the two ingredients to my addition that I need?
Num1 and num2.
So I've got num1 I can drag in, and num2 I can drag in. Okay, I've added them. So?
And then you want us to output that.
Okay, so what I can do is I can get rid of my say block before, sorry, get rid of my join hello and answer block before. We're not doing that now. What I'm going to do, instead of saying hello world, I want it to say what the output of this block is. So now let's connect it up. Ready for us to give it a try? Okay. So what number should I put in? 47. You've got to pick two numbers that you know how to add, though.
32.
Okay, what's 47 and 32?
That's a good question. 39.
Okay, let's try that. And indeed, our program outputs 79. So that is our example of our very first algorithm. Can we have a round of applause? Now, there are a whole lot of different things that you can do with Scratch. While it might look like this is awfully simple, all we've done is add two numbers. In fact, I have something that I prepared earlier to give you a look at. Let's leave page. And I can show you a game that I actually made. Now, partway through making this game, I ran into other things I had to do, but I attempted to make a version of Mario. Ooh. As you can see, the physics is a little iffy. So let's start that again. I think the computer's lagging a bit. I'm going to reset Mario. Let's go see inside. Come back, Mario. There we go. Okay, there's my Koopa. Ah, okay. We've got some more reasonable physics behavior now. Ooh. And you can see I've even got a block that I can hit and bounce off. Ooh. And let's try and get the Koopa. Ooh. I'm not very good at this. There we go. So while the ingredients we've seen look really, really simple, just using simple ingredients, you can build a very complicated program that does a whole lot of things. So for example, in order to make this work, I had to code in the equations of motion for physics, for example. So I put in gravity equals 9.8 meters per second, and I said, okay, for every second that passes in this thing, update the speed of Mario vertically, depending on how fast he's traveling. And you can actually see that in the code over here. With set Mario direction, I have these very complicated blocks that say, okay, figure out the angle that Mario is going based on the inverse tan of the horizontal velocity and the vertical velocity, and figure it out all that way. And you too could build one of these programs just using what we've given you already, plus some of these different tools on the side. So I'll show you a few more of them just so you have some extra things to play along with. Let's go back to a new file, because I think we probably want at least a little bit of motion. It's not too exciting if it just says something. So I will put in an event block. So when start clicked, we'll take a motion block and we can do move 10 steps. So we'll try this, move 10 steps, and you can see now my cat moves every time I press the green button. But that's not exciting. What might be a little more exciting? Controls would be really good. So let's try under sensing, I think it is. So let's try an if block, and this is going to allow us to test if a given key is being pressed. So if key space pressed, then move 10 steps. So let's try this. So now I'm going to press the space, and nothing's happening. Why is nothing happening? Okay, who said that? Remind me your name? Gabriel, okay. So Gabriel says because it's not activated. Oh, that seems funny. Okay, it looks like I've activated it. Let's pass the microphone on to someone else. There we go. What was your name?
Ashna.
Ashna, awesome. So let's follow the logic explicitly in here. So when I press the green button, if key space pressed. So is the key space pressed? Is the key space pressed? Is the key space pressed?
Moving if it is. If it is, it's not moving.
If it is, it's not moving. But when I hit the button, the green button, that's when it checks if the key space is pressed. So what might I need to do to actually make this useful? Because it's only checking at that instant when I press the green button. So what's something else that I could potentially do to make this work a little better? How often should I check if the key is pressed? Should I just check it the second I press the green button?
Yeah.
So think about, like, have you ever played a racing game before? Right? You know when you press the arrow key? Does it just look for the arrow key once when you start the game?
No.
How frequently is it looking if you press the arrow key?
Every time it needs to move.
Yeah, and it's checking that probably really frequently because every time you press it, it seems to respond. So maybe what should I be doing with this?
Press this space more frequently.
So it's only checking once. So what we need to do is we need to make sure that it's actually checking lots and lots and lots of times. Because if it's not checking lots of times, no matter how often I press it, if I haven't pressed it that exact 1 second when I press the green arrow, nothing's going to happen. So we might need to introduce a loop. And a loop is going to be exactly what it sounds like. It's a way for us to repeat certain actions. So let's put in a forever loop. Now this loop is not going to exist in Python, but it will in Scratch, and there'll be some adjustment here. But forever, if key space is pressed, then move 10 steps. That sounds a little better. Now our program is going to keep going, and it's going to continuously check if the space bar is pressed. If the space bar is pressed at any time when it checks, then it's going to move us 10 steps. So now let's run this. Ah, and there we go. It's moving. Can we have a round of applause for Ashna who figured this one out? Okay, so now we're going to take a brief interlude and go over to Grok Learning, where we're going to use the Blockly programming language, which is very, very similar to Scratch, just a little less graphical, and with the added bonus that it will actually produce some Python code for us at the same time. So you can see the matchup between the Blockly language and the Python language. So let's check that out. I'm going to go to the class website now, COMP10001.com. And hopefully some of you have seen this already. It's linked to in the LMS. And I'm going to click the assignments button in the corner. And log into the LMS. There we go. And here is our list of Grok worksheets. Now, if you watch the week 0 lecture, I will have spoken a little about how these are assessed, but essentially the idea is that there are worksheets every week for you to complete and build up your programming skills. Just like practicing piano, we're going to be practicing coding in a similar way relatively frequently. So let's click on the very first Grok worksheet. And hopefully Grok is actually, oh no, auth signature failure. So some of you may see this when you try and use Grok. This is a known problem. We are working with Grok to fix it right now. They've just changed a whole bunch of things on us last minute. So instead, I'm going to go to the Grok website directly. We will fix up the LMS ones. Bear with us for a day or two while that gets sorted. And so I'm going to log in directly. Okay, that is not happy either. Try Melbourne. Okay. Grok is unhappy at the moment, so we are going to have to get back to you on that one, and we will just keep playing with Scratch for the time being. On that note, if Grok is not working by the time that you're meant to have assignments going, number one, this is Grok's fault, not our fault, but number two, we will make sure that you don't end up with any negative ramifications. We might get you to do a Scratch exercise in the very first week if Grok is still not up and running. So don't worry about that too much. Okay. So the other thing I just want to note that the slides that we are going to be using in this class are also the result of contributions from a lot of people. So the slides with the ducks on them, these are courtesy of David Malin at CS50. They give permission for anyone to use and adapt their slides. And the slides that you're going to see from some of the other lecturers in this course were originally created by Tim Baldwin, who is now the provost at the Abu Dhabi AI University. I've forgotten the full name, MBZ AI University, along with a whole bunch of other UniMelb lecturers. So now I'm going to switch over briefly to our other set of slides from the other lectures, and these are the ones that you'll probably see particularly when it's not me lecturing, because I tend to use my own sets of slides. So let's pull those up, given that Grok isn't working, and we will carry on from there. And this, for those of you who downloaded the slides earlier, this is the second pack of slides. And we were meant to be doing more Grok stuff, but I guess that will have to wait. So now we are finally ready to start talking a little bit about Python. Now, Python is unfortunately not going to be as syntactically friendly as Scratch was. The reason is that Python we're going to write textually from Scratch, so it's going to involve you opening up a text editor of some sort or typing words into Grok, and that's going to be very, very sensitive to slight typographical errors. So whereas in the Scratch and Blockly languages, the blocks are already pre-made for you, if you were to type in say, but in Python you've called the function say with a capital, or you have called it say, says, S-A-Y-S, because you've misspelled it, the computer is not actually going to understand and be able to correct it for you. So that's why we try and get you introduced at the very, very first week only to these graphical programming languages. And then in Python, you're going to have to start to interpret error messages that the computer gives you about typos that you've made and about other things that you might have done wrong. Now, this does not mean you're a bad programmer. In fact, I'm sure as Giuseppe can attest to, programming errors are a part of every single time you sit down to write a program. I don't think I can recall a single time that I've written a program in my life where I've not had a bug. In fact, I'll tell you, given that we've got a little time, I'll tell you a story from my PhD. So I normally tell this story in FOA, so you might hear it again next semester. But I was sitting with my PhD advisor, and he put $100 down on the table in front of us. And he said, there is a whiteboard. I will give this $100 to anyone who can successfully write an algorithm with no bugs to do a search through a list in a particular way on the whiteboard. And there were 7 PhD students in the room there. We were all at a pretty fancy university, and we all one by one took a try at writing it on the whiteboard. Out of 7 PhD students, how many won the $100? 0. So these are people who've spent years studying it, being taught by one of the world leaders in this discipline. 0 could successfully write the program correctly the first time. And so finding these bugs and debugging is an important and core part of programming and one of the skills that you will have to develop. So if you were sitting at the computer for hours trying to figure out why your program isn't working, you're programming correctly. Now, this may be a little frustrating, and as you get more experienced, you'll find ways to spot some errors faster. So now, if I were to say, take a look at some of your code, there's a good chance that I would be able to find it after a minute or two, even when it takes you an hour or two. But this is, again, a sign of experience and a tool that you will develop as time goes on. So this frustration is normal, it's expected, but if you come and get help from us, and occasionally we'll ease the way from you, we can hopefully ease the frustration enough so that you can learn from it. So the next thing that we're going to go over is some basics of programming that we're actually going to need to do. And given that Grok isn't working, I'm actually going to show you some of these demos on a different website, cs50.dev. Now, cs50.dev is just a website that provides a built-in environment for running programs directly. So let me log in, and this will take a minute. And the first thing that you see once it's actually loaded will be an interface that allows me to edit text files and type in commands directly into the program. And so you can see here, I already have created a file, it's still loading, called hello.py. And when we are done with the loading, I'm going to stall for another few seconds. When we are done with the loading, there we go. We'll see an interface where I can type some text in a window. I can type some text in this window here. And then I have files and folders just like you'd see on an ordinary computer on this side. So I've gone ahead and already created a file called hello.py, and I'm going to delete it just so I can do that again for you from scratch. So I'm going to right-click on my folder that I've created for FOC, new file, hello.py. And a .py file is nothing special. It's just going to be words. It'll be just if I'd called it .txt. But .py is just a reminder to ourselves and a reminder sometimes to the computer that what we're going to put into this file is text that should be in the Python programming language. But there's nothing special about it. It's just letters on the page. What turns the letters of the page into the program is a special program called the Python program that takes in text and outputs the code for the computer in that assembly language and eventually sets those switches internally, those electrical switches, to make sure that our program actually runs. So I'm going to press enter and create hello.py. And now I'm ready to start programming. So the very first command that we are going to use in Python is the print function. The print function comes built in, and it is just like the say block in our Scratch and Blockly languages. So the way we are going to indicate what we are giving input to for the print function is we're going to use these two circular braces. So the circular braces indicate that whatever we put inside the circular braces is going to be the input to our function. Now the print function, as I mentioned before, is just a historical way of saying we want something output to the screen. And because this is our first program in Python, what am I going to print to the screen? Hello world, okay. Now you'll notice the other thing that I've done is I've included these talking marks, these punctuation marks around the words that I'm using. And this is to indicate to Python that I actually want it to use these words directly. If I had written, for example, without the talking marks, something like num1, that would tell Python that what I want it to do is I want it to print out the contents of that variable. Remember, a variable was just a way for us to store something in the computer's memory attached to a name. But I don't want it to print a variable, I just want it to print some words. And so those words are going to be what we call a literal, because we want the computer to take it literally. We want it to actually print the words hello world. We don't want it to go looking for a variable called hello world. We just want it to print the words hello world. And so the way we write a literal, made up of letters and characters and that we want it to print to the screen, is just by using those talking marks. So let's do hello world, and now I've saved it. I just hit Command S on my keyboard, but it hasn't done anything. Why is it not printing hello world? What haven't I done yet? I haven't run it. I haven't actually told the computer to do anything. Right now this is just a text file with some words in it. And so the command that I'm going to use is I'm going to use the Python command, and as an argument to the Python command, what I mean by an argument is an input to the Python command, I'm going to tell it which file I want to run. Now once Grok gets its act together, you won't have to do this because Grok will automatically do this part for you. But for the meantime, I'll show you how to do this. So the first thing I'm actually going to need to do is I'm going to need to go into my Foundations of Computing directory. And so the way I tell the computer to enter the directory is this command, cd, short for change directory, and I'm going to type in FOC. Okay, so now you can see that my terminal, where I enter commands directly into the computer, is updated to put me inside the FOC directory. So now inside the FOC directory, I have my hello.py, and I can run it directly. So Python hello.py. Hello world, wonderful. And you can see that it's automatically added a new line for us so that the computer is once again ready to accept input. Now, just like the Python command allows us to enter programs into the computer and commands, the terminal also has a whole bunch of built-in instructions, but also allows us to write our own programs so that we can instruct the computer on new programs that it might make available. So if I had a program called goodbye.py, I could now run python goodbye.py in the terminal as well, and I've now added functionality to the computer. And this is the whole aim of programming, is to slowly build up these tools and add more and more and more tools such that you can start to compose them. And indeed, it's just a program just like the ones that we've written now, which are what makes the computer work, and the terminal itself is also one of these programs. So it's programs built on programs built on programs. So we've talked a little about algorithms so far, and we're going to finish off with a bit more of a discussion about algorithms, literals, and variables, as well as some of the types we use in Python before we carry on with that next week. So for an algorithm, there's no single definition that actually makes it really concrete. We've talked intuitively about some of the properties that an algorithm has, but there are a number of features which will at least help us to identify things in category of algorithm, not an algorithm. Dog, not an algorithm, doesn't run code. But here are some other properties that we might consider. So for example, an algorithm should consist of a set of steps that we can compose together in order to solve a problem. An algorithm should also finish after a set amount of time. If our algorithm runs forever, then we probably don't have a good algorithm. And finally, it also must be universal in the sense of it shouldn't be an algorithm that just works for one particular set of inputs. It should be generic. So it shouldn't just, an algorithm is not hello world, but we might consider the program that we wrote before that asks for someone's name to be more algorithmic, because that works no matter who the person is that's running the program. So that's what we mean when we say universal. So some other things that we might want to do in Python, we might want to do the types of arithmetic that we did before in Scratch before when we added those two numbers together. So Python comes built in with a whole bunch of different arithmetic operators. And when I say operator, we use the word already in Scratch, I mean a symbol that we can use to perform a certain mathematical operation. And so we have our addition operator, our subtraction operator, division, multiplication. But we also have some different ones that you may not have seen before. So we have exponentiation, which is like 2 to the power of 3 or 3 to the power of 9. And the way we write that in Python is just with these two star symbols. And then we have these two other operations, which are definitely more computer science-y in flavor, and that you'll see as you get to more higher computer science classes and maths classes. And these are the modulo operator and the integer floor division operator. Now, essentially what these are, they're a way of doing like elementary school or lower high school math. So you'll remember your teacher might have asked you to do some simple arithmetic, so 5 divided by 2, except instead of just giving you 2.5, she'd ask, okay, how many times does 2 fit into 5? So how many times does 2 fit into 5? 2. And what's the remainder? 1. So this is the type of operation that our modulo and integer floor division are doing. So the floor operator is going to tell us how many times does this number fit into another number. And it's going to give us only in whole numbers. So for example, if we do 5 floor division 2, that's going to give us 2, because 2 fits into 5 2 times. If we were to do 5 modulo 2, that'll give us the remainder, and that's 1. And this ends up being fairly core to computer science because it helps us deal with the fact that the computer doesn't have infinite memory. Ultimately, when we use up all the memory inside our computer, we're going to start wrapping around back to 0 again. So if you imagine you have 3 switches, they can be all set to 0 or 1. You flip the first one to 1, you flip the second one to 1, you flip the third one to 1, and now you've run out of things to flip. So if you need to go back to another number again, what the computer's going to do is it's just going to flip all these switches back down to 0 again. And so this kind of wrapping around behavior is well captured by the modulo operator. So you'll start to see this quite a lot. Python does follow as well, just like in high school, an order of operations. So this is going to associate the order in which the different operators are processed. But of course, just like in high school maths, or who's doing Calc 1 or linear algebra at the moment? Anyone? Yeah, so you're going to be seeing this. So you can use parentheses to change the order and give certain things higher priority. So if you haven't seen it before, I'm not here to teach you high school maths. But if you want to refresh your memory, there's either BODMAS or BOMDAS is the acronym used in English to remind us of the order of operations in which we have to process a mathematical expression. So give this a try out in Python. However, because Python has more operators than just the ones that we used in high school, we need to further build on our order of operations and add some more exceptions to it. So following this order, we're going to first do exponentiation. Exponentiation is going to come first. Then any unary operators, which means they're an operator that only takes in one argument or only works on one thing. So for example, -4 on its own is going to happen if the negative sign is, it's not like 4 minus 3. If it's just -4, that's going to be that kind of priority. Next up, are binary operators, operators that take in 2 arguments, so like 3 plus 4. There are 2 arguments there. And then finally, binary addition and subtraction. Okay, we're not going to talk about those for the moment. So let's try this operation according to our rules. We're back on speak up again. What is the result of 2 to the power of 3 times 2? And let's look on speak up. There's speak up. And I'll open the poll. Okay, we seem to have a fairly strong bias here towards -16, so let's give it a try. So let's go back into our program, and let's write this expression and see what happens. So we do indeed end up with -16. So feel free to give this a try on your own, play around with the different order of operations, and see how Python is actually going to process things and in what order. So you can also, as I said, modify the order of things. So for example, if I do this, I'll get -15 because the +1 is processed at the very end. But if I were to put parentheses around this, you can see that's changed because I've overridden the order of operations with my parentheses. Okay, let's skip that one. So for the last thing that we're going to do today, let's see what we are going to be able to do just with the operators we've got so far. So can we calculate n factorial just with our operators that we've got now for an arbitrary n? Is there a way to directly do it? And I will make sure I've opened the poll, which I sometimes forget to do. So open the poll. So can we do factorial just with the operators we've seen already? So we have a bias towards yes. That's the question again. Okay, next one. What about the ith Fibonacci number? Can we do that just with the operators that we've got so far? So I'm going to reset the poll somehow, if I can figure out how to do that. Give me a second to reset it. There we go. Reset. Okay, I'll make a new poll. That's not... Okay. Yes, B, no. Where is this one? There we go. Fibonacci. Okay, so most of you say that we can calculate the ith number in the Fibonacci sequence just with our operators. And then last one, is it possible to break Python just with the numbers that we've got, with the operators that we've got so far? So I'll make one, break Python, and A, yes, B, no. Open to interpretation. Can we break Python just with the operators that we've got? And we have more yeses than nos. Okay, so I'm actually going to leave those answers for you for next week, where we'll continue on with the core content for the class. For now, have a think about this over the weekend. I will give you one hint, which is that the answer is partially yes and partially no. The operators that we've got are necessary, but they may not be entirely sufficient without some other stuff. Thank you so much, and welcome to Foundations of Computing. Elizabeth, what's up?